So coming back, so if you so you have gathered that, okay, in the case of LDV, the two beams intersect and you get an interference pattern, and it exhibits constructive and destructive interference, and the fringe spacing is given by this, where this theta is basically the included angle, or the angle between the two beams. As a result of that, the particle which is traversing the fringes will scatter alternatively high and low intensity values, and the frequency of the light intensity changes can be hence used to determine the velocity of the particle normal to the interference fringes. Remember, this is the velocity normal to the fringes, and this is the formula. So this is very easy. If you can measure this, this is of the order of 1 to 100 megahertz. The lambda is well known, so it should be possible for us to calculate. So now if you look at the fringe model, the Doppler signal, so the particles that are traversing the fringe, if you look at that is the fringe, and the particle just goes through the fringe, through this measurement volume, so to say, it shows an amplitude modulation at a frequency which is linearly proportional to their velocity. So this is Fd, and this is proportional to the velocity component, which is normal to the fringes, fringe lines. And it is related to it by a purely geometric factor and the wavelength of the laser. So the light intensity, if you look at it, they fluctuate like this. If you see the intensity of the light, it fluctuates like this. So there is high, low, high, low, high, low, and this varies with time because of the particle transit. And this amplitude modulation happens at a frequency which is linearly proportional to the velocity. So this is how what a detector should actually see, because here at the dark fringe it will scatter less light, at the bright fringe it will scatter more light, so the light intensity therefore changes quite a bit. Now if you look at the measurement volume now, you will find that this is rather interesting. So dx and dy, okay, they are more or less of the same order because the theta angle is not that much, so they are of the same order. So dx and dy, they are kind of very similar, so you can calculate this, okay. And but the dz, because it has got a sine theta by 2 component, okay, so this shows a little bit of an enlargement along the direction, along the optical axis direction. So it more resembles a cigar type of a volume, in which the z is actually extended, where x and y are of very similar orders. Okay, so the measured velocity that you measure is an integrated value over this measurement volume. Now this measurement volume therefore is not a very symmetrical measurement volume. It has got lower dimensions on the x and the y side, higher dimensions along the z, and this is how the fringe lines also appears. So the measured velocity is an integrated value of the measurement volume. Okay, this is the important part to know about this. All right. Now if we look at the Doppler signal, so due to the Gaussian intensity profile of the beam, as you can see, this is the Gaussian profile of the first beam E1. This is the Gaussian distribution profile of the beam E2. So these beams now start to interact in this particular zone. But this zone, if you see, it's not very homogeneous, so to say. So for example, of a particle which is going through the middle, it will see at the edge, it will start to see the burst, okay, and then as it passes through the middle where the two beams have kind of intersected with each other, it will see more bursts, I mean this modulation, and then it kind of taps off at the tail. It will kind of show so a particle which is passing at the edge, for example here it sees only a single beam, then it starts to see, it comes to the edge of the beam, and then it starts to see the second beam. So this amplitude modulation or the intensity modulation for a beam, for a particle which is passing at the edge of this measurement volume, will be very different from a particle which is passing through the center of the measurement volume. So due to the Gaussian intensity profile, the amplitude varies, the signal amplitude varies as the particle moves through the measurement volume, and the signals for different particle trajectories are actually different throughout the measurement volume. Okay, so you see at the edge it is something different because here it sees one beam, then it sees the other beam. There is a very small degree of overlap that may be actually there. In some cases there it may be just seeing one beam and then the other beam. So all these things have to be taken into consideration when we actually show this. Okay, so this is rather interesting. If you look at it that way, it is rather interesting, and this is what actually happens. Okay, so more on this. If you consider this is the kind of the interference fringes. Again, there is a little bit of German here. This is from Professor Tropia's lecture notes. So if you look at, these are kind of like slices, three-dimensional interference slices, so to say. So what happens is that as the particle, so this is x and y, and then this z, as it passes through this measurement volume, this is a typical what we call a Doppler burst. So you can see that there are, depending on how the particle is moving, there is an amplitude modulation. When the modulation is when the modulation is absolutely, if this goes to 0, then of course you have a modulation which is kind of 1. So this is the kind of typical signal that you get. So if you look at it carefully, this signal has got a varying mean or an envelope function, something like this, and then there is a modulation that sits on the top of it. It is almost like the ratio between a DC amplitude and an AC amplitude, and this will be a function of the particle trajectory. The amplitude of the AC part will be maximum for trajectories in which the beams exhibit equal intensity. So this is required for the best signal to noise ratios. You have an enveloping function, and then you have a fluctuating function on top of it, pretty much like a DC and an AC component, right? So if you now look at it, the ratio between the DC and the AC amplitude is known as the modulation depth. Now, when the modulation depth, if you look at it carefully, it is 2A1 into A2 divided by A square plus A2 square. So when you actually have your A1 and A2 to be the same, okay, this modulation depth becomes equal to 1. Or in other words, if you look at it, when this goes absolutely at the end, okay, so then this amplitude actually becomes equal to 1. Other than that, if that is not the case, then you get something like this. So if you look at, this is the amplitude for this, and this is the amplitude for the AC part of the signal. All right. So if you now kind of classify this, you will see that there is this, this is the total signal, and this is the mean, some kind of an offset basically, and then this is the fluctuating signal. So for waves of equal amplitude, the modulation achieves a maximum value of 1. The signal is then low pass filtered to improve the signal to noise ratio. So this is what happens when the particle passes through this Doppler fringes. Okay, so how this happens is that you have a Doppler burst and your photodetector sees something like this. Okay, then you pass it through an amplifier, and then you pass through an adjustable bandpass filter. What the bandpass filter does is that there is a high pass filter which removes the low frequencies which is arising from the Gaussian intensity profiles of the beam. Okay, so that is the envelope. And then there is a low pass filter which removes the high frequency electronic noise that are kind of embedded into the system. So you pass it through this kind of a filters to basically generate the final output. Okay, so you can see that there is a DC component and then there is an AC component. I want to emphasize once again that this is the total signal, this is the envelope, and then you have the pedestal function, and this is basically the modulation. And the modulation depth is equal to 1 when A1 and A2 are basically the same. All right. And also remember that the particles passing through different areas or different trajectories across the measurement volume shows different types of signals, so to say. All right. So this is how the photodetector assembly actually occurs. So in the measurement volume, so the measurement volume is defined by the amplitude of the modulation and the region in which the velocity measurement is performed. Now, the size of the measurement volume is usually understood as a region in which the modulation amplitude is larger than e to the power of minus 2 of the maximum value. Thus, the measurement volume also depends on the scattering characteristics of the particles. So, this is important, right? Because you know that we are basically putting certain cutoffs. So, it normally, any in the two intersection of the two beams, that particular volume, you can have many types of, the particle will scatter. But then if you place certain filters in place, which is basically rejecting, low intensity versus high intensity, then you are basically pre-selecting only a part of the measurement volume. That means the signal from all other parts of the measurement volume will be basically ignored, or you are throwing them out. So in effect, your measurement volume or the actual acceptance level of the measurement volume may be actually smaller than the actual measurement volume that are defined by the crossing over of the two beams. Okay. So the measurement volume, as you can see, is IAC by IAC max is e to the power of minus 2. So according to the Gaussian intensity profiles of the beam, the measurement volume takes an elliptical form with these following dimensions that you see over here. Okay. So these are the dimensions of the measurement volume. And these dimensions are basically shown over here. Okay, so this A naught and B naught, the delta T is basically the time. And this is the signal characteristics as the particle passes through it. And you can see that IAC by IAC max is e to the power of minus 2. And so all these characteristics are actually marked here. Okay. So you pre-choose, you define what is important for you, and then you can down select only a portion of the measurement volume. So the detection volume, therefore, since the intensity of the scattered light depends on the particle size, the signals will be detected when they exceed some predetermined amplitude, ID, for example. So the detection volume is the volume in which the particles exceed this threshold, and therefore it is dependent on the particle size. Okay, so the half axes AD, BD, CD, and the detection volume can be expressed like this. So this is the max. Okay, and this is ID. So this is some predetermined value, predetermined amplitude, and so the detection volume is the total volume multiplied by this particular term over here. All right. So this is the expression for the detection volume. Okay. So in other words, the relation between the measurement and the detection volume is therefore like this. You can see the actual detection area is somewhere here, whereas this is the total measurement area. And these are some of the relationships. Okay, this you can always work out, and we can go through the paper as well. So this is only a small portion of the measurement volume, depending on what you have chosen to be your ID. And this is a predetermined value that you are basically supplying to your kind of a system. Okay, so this is important. So what we have learned that what is a DC component and what is a AC component, how the detection volume is different from the measurement volume. Okay, and we have also seen that how you can use filters basically to throw out the high frequency electronic noise versus the low frequency, the shape profile, the shape or the pedestal function. So the measurement volume is therefore, as you can see, is given by this, is defined by the amplitude in which the velocity is measured. So this is the detection volume, and this is how it is calculated. So it depends on the scattering. The actual detection volume is actually smaller than this, just because the way that we have chosen the predetermined threshold. Okay. Now, if we go to the optical system that actually measures, that is actually used for measurements, what we do is that we have a laser, and then you split the laser light into two using a beam splitter. You preserve the coherence or the phase, and then you pass through the lens, and then you focus it to a particular measurement volume that we already know. Now you can measure the whatever, after that whatever happens is you are not concerned about that, but then you are focusing your photo detector and you are either measuring, this is a typical side scatter, this is a forward scatter, and this is a back scatter. So you are measuring this kind of, this side scatter can be at any particular angle. The forward and the backward scatter is like this. The various configurations therefore are possible to actually do this. The interesting part is that because there is a linearity with the frequency shift and the velocity, this becomes a very easy tool to use it with. Okay? Now, in the two beam configuration, if you look, the forward scatter is a very simple problem. So you have the laser, you divide it using a beam splitter, you preserve the coherence of the phase, then you use a thin lens basically to focus it at a particular measurement volume with all the particles going through that measurement volume, right? And then you have a receiving end, which is a detector, which also uses a focus is on that particular measurement volume. And then this is what you collect in the forward scatter. The forward scatter, as you know, can be quite high, 100 times higher than the backward scatter. But the backward scatter, how it is done, that the detector and the laser are all in one unit. So it is backscattered and it is fed by another optics where it goes into detector, photo detector. The advantage of forward scatter is that it is very simple. The backward scatter requires a little bit of engineering, but at the same time, this has got advantage that this can be integrated within the optical system, and therefore you don't require external alignment and maneuvering, which is a big deal, because in the forward scatter you need to, or any side scatter as a matter of fact, you need to put the receiving unit so that it is perfectly focused and it can come from any particular direction, etc., etc. So this needs to be a very comprehensive unit, okay, and it requires alignment, but this is like pre-built by the manufacturer, and you cannot really, you don't have to do anything. It is already adjusted or pre-aligned. So therefore, though the magnitude of the scattered intensity is lower over here, you basically can live with it if your experimental setup becomes a much easier proposition, particular case. All right. So now we go to the case of the transmitting optics. Now in the transmitting optics, what you see over here is something interesting. So this is how you now transmit the transmitting optics. So the measurements, the size of the measurement volume is usually an important parameter. It is determined by the laser beam diameter, which is given by 1 over E of the maximum intensity. So the minimum beam diameter is known as the beam waist. So let's just look at this. So you have an incoming beam which has got a beam diameter or beam waist of 2RW1. This expands, and then there is a lens which actually focuses it to another beam diameter which is 2RW2. This is actually 2. Okay, and there is Z1 and Z2, and then there is the focal points. So if you look at the second beam diameter, okay, over here, okay, so this is DW, this is DW2, and this is DW1. So DW2 is therefore given as 4 by pi f into lambda. F is a focal length, lambda is a wavelength, divided by DW1. So this is DW1. So in other words, what you can see is that DW1 is in the denominator. So smaller the value of this, more will be the value of this. So you ideally want this to be large, this to be large. So that means you need a large beam diameter, okay, for you to have a very small spot size, a very small DW2. Now, this is of vital importance because in many cases, you want to focus your beam to a very small location. Why this is important? Because, the small scale location, because for example, you want to, place it in a flow where you want to have your spot size or the measurement volume, so to say, of the order of say tens of microns. in order to achieve this, what you need a very large D, because all the other things are kind of given. So a very large D. So this large D can be attained by using a beam expander, which is used as a collimator. So it actually expands the beam out. Okay, and therefore you can kind of focus them to a much smaller location. So this is rather interesting. So what you do normally, you have this coming from the laser, then you use a concave lens assembly to basically expand this out. Okay, and then you use a thin lens, a collimator, basically to make it parallel, and then you use a thin lens to basically focus it at a particular point. So you are concerned with this large D, which therefore is what actually can give you a very tight spot. Okay, so these are some of the interesting features, because you sometimes need that very small measurement volume, so to say, depending on the type of experiments that you are doing. Okay, because remember, it is volume averaged over that particular measurement volume, so you need it to be very small to get the kind of fidelity that you want. Because remember, as your particle passes through it, if it has different velocities, for example, if it passes through, then if it has different, it is all averaged out in that particular measurement volume. So you need to have large intensity there, and you need to have the particles go through that measurement volume, so that you can assume that it is small enough that spatially in that particular region of interest, the particle's velocity does not change by much. So this is the interesting part, and this depends on what is the incoming diameter of the is. Okay, so the transmitting optics, for example, the size of the measurement volume therefore depends on the beam diameter before the focusing lens. This is important. The size of the measurement volume, as this particular expression shows, so it depends on the beam diameter before the focusing length, the focal length of the lens, and the distance between the two beams before the lens. These are therefore the parameters which can be used to change the measurement volume. But to get a tighter spot, you need a beam diameter which is large, and that is where the beam expander comes into the picture. And then, of course, use the collimators and other things and thin lens formulas. Okay. So, for example, take a look at this table. So, the laser beam before it goes to the transmitting lens, say 1x means there is no expansion, is 1 millimeter. After expansion, it is like 2 mm. So the beam separation before the transmitting lens is 5 centimeter and 10 centimeter, for example. The diameter of the transmitting lens is of that order. The focal length is 310 mm. The intersection of the beams is about 9 degrees, and this is about 18 degrees here. The length of the measurement volume is 2.5 mm. Okay, and 0.63 mm you go on to the beam expansion. So you can see how much reduction we had, because if it gives you and the normalized light intensity goes up by 4. This is because if you reduce the diameter of the laser beam, if you reduce the measurement volume, then what will happen is that because the same intensity is now captured within a lower volume or a lower surface area in that particular case, this has got therefore a d square dependence. So therefore the light intensity in that particular spot goes up by 4 times if you can reduce it to half. If you can reduce it to half, that is what is going to happen. So if you see the measurement volumes, these are off by a factor of 4 kind of stuff. Okay, so you can see the normalized light intensity, why it goes up when you actually have a beam expansion, and the measurement volume also becomes very tighter. But for that you need the beam expander. That means the laser beam with beam expansion to be rather large. So this is the caveat. So when you are trying to focus this Gaussian beam optics, you need to take these into consideration. This is all because of the Gaussian beams and because of the intensity profiles that it carries. So once again, if you take a look, this is the intensity profile the Gaussian beam has. So naturally, the particle sees different intensities at different points in time. If these would have been of the same intensity, then it would not have that envelope function anymore. Okay, the envelope function would be actually redundant if these were kind of all had the same intensity, but it is not. Okay, so that is the most crucial part of the argument. So we have talked a lot about the transmitting optics, therefore, that how the beam expansion actually increases the laser beam diameter. As a result of that, you can focus it to a much tighter position. Okay. So if the beams do not cross at their respective wastes, an error can occur because the fringe spacing is no longer constant anymore and the fringes are not parallel to each other. So this leads to different measured velocity depending on the trajectory of the particles through the volume. So, this is called longitudinal fringe divergence, and this is the transverse beam fringe divergence. So that if this happens when the beams do not cross at their respective wastes. So what are the wastes over here? The respective waste will be shown in this particular plot here. So these are the respective wastes that we are actually concerned about, right? So now in the next class, we will talk a little bit about the coupling. That means how the receiving unit actually uses optics and fiber optics and other things to collect the signal. So you can see, but you can roughly get an idea that it is a linear one-to-one correspondence between the frequency and the velocity. And the velocity is perpendicular to the optical axis. This you should keep in mind. Gaussian beams require special kind of focusing, and the beam diameter, more the beam diameter, tighter spot you can actually focus it. As a result of that, you can get a very tight volume. You can get a very tight volume. And here we are essentially looking at the beat or the interference so that we can calculate what will be the velocity of the particles. And the particles, remember, they follow the flow field. So we stop here.